So yeah, I've already been introduced, so that's great. Actually, I don't have my speaker slides showing. Can I have speaker slides? Okay, well, before I get speaker slides showing, which I do need, if you need to ask me anything, just take a picture of that real quick, and you can ask me at the end of the talk. My speaker notes aren't showing? So, okay, can we have just a few minutes then? Because I'll need my speaker notes, sorry. What's that?
Is it on your slides right now? Is it in your?
ALGORITHMIA by heart, right? So I can talk a little, oh, never mind, sorry.
There you go. Is that what you need?
Yes, perfect, thank you so much, I appreciate that. Okay, so now we're in business. So I'm a developer solutions engineer at ALGORITHMIA. So ALGORITHMIA, we really focus on scaling and getting your data science models into production fast. So we want data scientists, whether they're individuals or enterprise customers, to be able to deploy their models really easily so they can focus on data science versus DevOps. So yeah, go ahead and at the end of this talk, I'm giving a promo code. So we do have an open marketplace that anyone can join, deploy your models, check out, kick the tires of the platform, and then we also have Enterprise, which is a licensed product. And so definitely ask me any questions you have about that. So what we'll cover today is tensors, some computational graphs 101, basics of dynamic computational graphs. I'm not assuming everybody has the same background, so I like to do a little bit of the basics first. I'm going to go over why dynamic computation graphs are so cool, and the debugging awesomeness in PyTorch, because it's tied to the architecture of the graphs. Also, serialization in PyTorch isn't necessarily as easy or performant as serialization in Tensorflow, so I'll go over some of that too. And then of course, like the fun stuff is use cases. Okay. So PyTorch is an open source deep learning framework that was primarily developed by Facebook's Artificial Intelligence Research Group and publicly introduced in January 2017. So while PyTorch is still relatively new, users are rapidly adopting this framework. It's very modular, and it supports dynamic computation graphs, which I'll go into a little bit more in detail later. And that allows you to change the network, how the network behaves on the fly, right? So that's unlike static graphs where you have to define all your model architecture first before it's actually run, right? So it also, because you're not using a static graph, you can really step into the graph and debug easily in PyTorch. So and it's also, you're not using a separate API like TensorFlow, you're basically writing Python. And so it's a lot, the learning curve's a lot easier, even when you're comparing Keras with the TensorFlow backend to PyTorch. So PyTorch shares some C++ backend with the deep learning framework Torch, but Torch is written in Lua. Not as many people know Lua. The data science community has widely adopted Python and R. So PyTorch has become, readily adopted by the greater community. It really started out, though, with the research community being the early adopters. So the image shown on the slide is a popular image filter model, and it was originally written in Torch and developed by Wanyan Su and Tetsang Park. And they rewrote this model in PyTorch, citing the same or sometimes better results as the Torch version. So you're not sacrificing a ton of performance either when you're comparing those. So the major concern with some previous versions of PyTorch, if you've ever played around with PyTorch before, you might relate to this. It wasn't always easy to deploy in just any environment. So serialization, as I said before, it's a little bit, it used to be a little bit clumsy if you wanted to deploy your model outside of Python environment, so you would have to use onks. But with the PyTorch 1.0 release in early December, they've really focused on a couple of areas to help with optimization and helping really move it from research to production. So you can check out more about the release and the release notes, of course, but they're really focusing on a couple of those things, as well as so they're adding. So what they did, they merged Cafe 2 backend to PyTorch. They merged these projects. So they used to use Cafe 2 in production and PyTorch in research, but they really wanted to integrate the two for deploying models into production. But they didn't want to lose PyTorch's iterability, ease of use, and awesome debugging attributes. So they're also adding a ton of optimization features by expanding the API, such as adding the ability to configure memory layouts, such as NCHW or NHWC, which layout you want depends upon your hardware. So again, performance optimization. They've also released torch.jit, which is a just-in-time compiler, and that converts your PyTorch models into production-ready code using TorchScript. And again, that allows for interoperability with the C++ runtime. So this way you can export your super performant models outside of Python-only environments, because Python's not the fastest language. It's faster than R, but it's not the fastest language for performance. So note, they're also planning on adding better mobile support as well. So I think TensorFlow has TensorFlow Lite for mobile support. PyTorch is lagging in that area a little bit. 1.0, it was supposed to be shipped with 1.0, but it didn't get into that release, so. All right, so again, PyTorch has really gained a lot of traction. It seems like a lot of people are interested in it here too. So one of the reasons that a lot of people have kind of moved to, at least checking it out is that you really can quickly iterate on your models. It's really good for making tight deadlines, and a lot of that's due to its intuitive, imperative programming architecture. Again, it's really similar to just writing a Python module. So the framework is also extensible using scikit-learn and other common Python libraries. So you can extend some of PyTorch's main components, such as TorchNN and TorchAutoGrad, and you can even write custom C extensions. So again, as I mentioned, it's easier to ramp up versus some other frameworks out there, like Cafe or TensorFlow. So it's pretty easy to get started as a beginner, especially if you've already been working with scikit-learn and NumPy. So you can even run NumPy-like arrays on GPUs in PyTorch. So I'll tell you a little bit later why you might want to do that. But another unique aspect of PyTorch is that it relies on dynamic computational graphs. So that means that graphs are created on the fly, and you might need that because if you have varying input data length, that it's non-uniform length or the dimensions are non-uniform, then you'd rather use a dynamic computational graph versus a static graph for that. Because in a stat graph, you will have to predefine those lengths. But maybe you don't know what computational graphs are or dynamic computational graphs. So I'd like to cover the basics of those really briefly so everybody's kind of on the same page. So I'm not an artist, obviously, but I did draw this diagram for you just to give you a visual on tensors. I've given this talk at PyCon before, and so I was talking to a lot of developers. So while this is a data science conference, and you might know this already, I still am going to go through it a little bit. So deep learning frameworks like PyTorch and Tensorflow, and yeah, the name is a spoiler alert, use tensors as their data structure, right? So tensors are the main building blocks of deep learning frameworks, besides, of course, variables, computational graphs, and other architecture. But tensors are basically objects that describe a linear relationship to other objects, right? So these data containers can be various sizes, like you can see on this slide, and they're called different names. And so you might be familiar with them as vectors. That's a 1D tensor. 2D tensor is a matrix, 3D tensor is a cube, and so on, and they hold numerical values. So if you've worked with NumPy, then it's really easy to make the mental switch to tensors. You can think of tensors as ND arrays or multidimensional arrays. So we need to talk about computational graphs because, as I mentioned, that's a huge difference between TensorFlow and PyTorch is how they architect graphs. So deep learning frameworks all require computational graphs. And computational graphs state the order of computations that are supposed to occur. So computational graphs are just DAGs. They're directed acyclic graphs, right? So most of us are familiar with those. Computational graphs are directional, and they have nodes, which make up variables, such as tensors. And now in PyTorch, those variables actually hold real data, whereas in TensorFlow, they're just pointers. So, and then the edges make up the operations on those tensors. So on the slide, you can see the nodes hold variables, and each computation makes up a new tensor. So neural nets rely on computational graphs. And when the network is being trained, the gradients of the loss function get computed based off those weights and biases, and then the weights are updated using gradient descent, right? So this is done efficiently by the computational graph using the chain rule. And this is pretty broad, high-level stuff across deep learning frameworks. But dynamic computational graphs are, I think they're the cool kids of computational graphs. So PyTorch relies on dynamic computational graphs, which are built at runtime on the fly, which you can see a visualization of on the slide. And that's just from the PyTorch docs, so you can find that online. So as I said, TensorFlow and other static graphs, they create the static graphs that compile time. So with static graphs, it means your network has to be defined before it's run. And so if you want to make any changes to the neural net structure, you have to rebuild it from scratch. So, you know, I like PyTorch because PyTorch fails fast. You don't want to, be, hours, days in the middle and have your model fail. So I like my stuff to fail fast. But I'm going to go over a little bit more about what it means to actually be dynamic. So in PyTorch, each iteration is a pass of both forward and backward passes on the network on the batch size of inputs, right? So an epoch is one forward pass and one backward pass of all the training examples in your data set. So the number of iterations per epoch is equal to the number of samples divided by the batch size. So for each iteration in an epoch, a new dynamic computational graph is created in PyTorch. After each iteration, the graph is freed in PyTorch, meaning you'll have more memory available. I'll go into a little bit of the difference between memory management between TensorFlow and PyTorch a little bit later. But if you've played with TensorFlow, you do know that you have to be a little bit careful because it wants to suck up all your GPU, and sometimes you don't want that. So PyTorch records the values as they happen in your code in order to build a dynamic graph, as you can see in the slide. And you can just imagine what that means for debugging. PyTorch does this through a reverse automatic differentiation system called AutoGrad, which is used to calculate the gradients. So reverse automatic differentiation is simply walking backwards through the computation graph to calculate the derivatives. So you can see on the slide, this is a basic example, it's a toy example of using AutoGrad. So you could see that variable A, where we store our input, is a tensor. And you can either pass in requires underscore grad equals true flag, or you can set it in place with the requires underscore grad method with newer versions of PyTorch. And this will compute the loss on any tensors that have that flag set to true. Then we can backprop through the graph to compute gradients. So then after that, we can do some simple operations on the tensors. And at the bottom of the slide, you can see that AutoGrad computes the backward pass. You can also extend AutoGrad to make your own custom forward and backward functions. For example, if you're using rectified linear units as your activation function, you can customize AutoGrad for that. So, just to summarize how PyTorch does reverse automatic differentiation, is that the graph is created on the fly each time code is encountered, and with backprop, the graph will be dynamically walked backward, recalculating the gradient when you need it. Okay, so we know what tensors are, we know what computational graphs are, we understand what dynamic computation graphs are, but what makes them the cool kids? So operations in PyTorch actually modify data. Like I said, those tensors hold real data. So it makes it possible to debug your code within the graph itself and treat it like regular Python code. Meaning, due to its imperative programming architecture, you can set breakpoints in your IDE, you can print out values during computation, you can read the stack trace and actually know what part of code it's referring to. I use Java as well in Scala, and sometimes that's not so easy. And Tensorflow isn't as easy to debug as well. So with static graphs, like TensorFlow, operations are only references or containers, but they don't store any actual data when you're defining your graph. So it's it makes it a lot harder to debug. So also dynamic computational graphs allow you, as I said before, to have that varying input length, which is important when you don't know exactly how much memory to allocate to your inputs, like in natural language processing, for example. Sentence lengths vary. So if you're to create a sentiment analysis model, for instance, using RNNs, where you also have various input lengths and native control flow, it's easy with dynamic computational graphs, and they're more performant in PyTorch versus the TensorFlow APIs. I haven't seen the newest TensorFlow API for dynamic computational graphs. I've tried to find some benchmarks for you, but they don't exist yet. But so far, they haven't come up with a version that's as performant as PyTorch's, because it's native to PyTorch's architecture. So another great thing about PyTorch is that you can add custom logic easily within the graph itself using native Python. So note, however, if your custom logic is part of the model itself, and if you're serializing your model using JIT trace and PyTorch in PyTorch 1.0, it won't work. You'll need to use JIT Script, and I'll talk a little bit more about that when I talk about serialization. So of course, static graphs aren't all bad. Remember, static graph architecture, such as in TensorFlow, can be thought of as define the graph, run the graph once to initialize the weights, then run your data through the graph multiple times within a TensorFlow session for training. So this architecture allows for distributed computing, so you can run the graph several times on different workers. This is because since you define the graph before you run it, and each node is independent from one another, the computations can be run in parallel. So this allows for different computations to be done on CPUs, while others can be done on GPUs fairly easily. So static graphs also allow for easy optimization, because you can optimize the graph while defining it before you run it. The compiler is able to optimize the execution of the graph out of order, so it can process things in a super optimal way. So it's a lot harder for a dynamic graph to be optimized, since it's actually created on the fly as the code runs. So static graph architecture also allows for the graph to be saved with all its methods and functions for production, which is really helpful, and that's probably my favorite thing about it, just because serialization of models isn't the easiest thing in some frameworks. So there are so many benefits to both architectures, and which one you chose was previously dependent on whether you want the benefits of dynamic graph versus static. But again, with PyTorch .JIT Script, that enables you to save your model as a static graph, and then TensorFlow eager execution, and then TensorFlow fold, it gives you a lot of flexibility in choosing your deep learning framework. And if you do pay attention to the releases and stuff, those two projects are kind of converging on their capabilities. So the debugging awesomeness is a huge reason myself and coworkers love PyTorch. So due to the dynamic graphs in PyTorch, the tensors actually contain values and the operations can modify data. I probably said that 3 times, but it's a really important aspect of PyTorch. It means that you can use your favorite IDE to debug using regular Python. It goes really deep. You can print out the weight sizes or whatever you want from the tensor within the graph itself. Of course, you can add breakpoints, but you can even step into the forward pass or the loss function and see what's going on in there. So note, however, that for calculating the gradient, you have to use a different method, .register underscore hook to inspect gradients because that computation is carried out by PyTorch and not you. So all this is huge because when training a neural net, you don't want to spend all that time and money training only to get your error messages halfway through. Again, you want it to fail fast. Because this is deep learning, let's talk about GPU support for PyTorch. So in PyTorch, GPU utilization is pretty much in the hands of the developer in the sense that you must define whether you're using CPUs or GPUs, which you can see a quick example of on the slide. You're saying, hey, if I've got GPUs, use them. If not, use CPUs. Or if you're using torch.jit.load, and that's available in 1.0, you simply pass in your model and append the CUDA method. A note on GPU utilization in Tensorflow is that while you can explicitly define whether you want to use CPU or GPUs, if you leave it as default, Tensorflow will try to figure it out for you, which is, you think would be pretty nice. But if GPUs are available, it will defer to using them, and it'll also take up all available GPU memory. So while training, that's a lot of times what you want, but not necessarily in production. So you do have to configure TensorFlow a little bit to not, suck up all your GPU if that's not what you want. So because a lot of times you don't want it for preloading data or pre-caching data, a lot of times you want to do that on CPUs. So TensorFlow gives you a couple ways around this. There are configurations, as I said, and they're shown in the TensorFlow docs, how to allocate memory as you need it, or straight up limit how much each device you want to allow TensorFlow to use. Also note, TensorFlow session does not release the GPU, even when you close the session, so you have to kill the process to release the memory. This is due to TensorFlow allocating memory to the lifetime of the process and not the session. So yeah, I mean, if you've used TensorFlow, you've probably hit those bugs before, or not bugs, but you've probably gotten error messages that point to you having to look that stuff up in the docs. So in PyTorch, you can, going back to the PyTorch NumPy arrays, I mentioned that you might actually want to run NumPy arrays on a GPU. In the first line of code, you can see that we are specifying the device we want with torch.device. Super easy, again, just looks like Python. And then we're simply converting a 2D dimensional tensor of size 4 into a NumPy array. So I do want to note that torch.ones will automatically be created using CPUs, so you have to change it to using GPUs. And then you can simply pass in the specific device you want using the keyword argument. So again, what's the use case for this? Well, you might want to do some computational heavy data preprocessing and are in NumPy, but you can switch to using GPUs in PyTorch and then switch back to NumPy arrays when you're done. And besides data preprocessing and stuff, and then maybe some training, maybe you're using your own, you built your own model in NumPy, and I've definitely known people to do this, then you might want to, train it on GPUs, and you can do that with PyTorch. So another cool part about PyTorch and GPU utilization is that you can move everything from the content tree, including tensors, gradient position weights, basically every component in the network, and it can be transferred back and forth from CPU to GPU. You can see on the slide how easy it is to transfer a tensor from CPU to GPU in the forward function. It's not hard at all. It's, again, very intuitive. So benefits to this kind of flexibility with a network like that is for custom complex architectures. So some work should be done on the CPU and some on the GPU. So being able to optimize is really nice. Also, being able to clone and save your model state in host memory during training allows for easy checkpointing if your training deviates. So that's pretty important. You also can define how you want your model to get parallelized. I do want to note in every case, when you're going from CPU to GPU, CUDA copies can be really costly, so be careful where you take advantage of this feature. Also note that GPU operations are asynchronous, so when you're moving stuff around, you'll need to use the torch.cuda.synchronize method to wait for all kernels and streams to finish. Otherwise, it will be very slow to move things around if it's waiting for the model to finish. So those are just a few tips. All right, so the nice thing about GPU utilization in PyTorch is the fairly easy and automatic way of initializing data parallelism. So using, as you can see on the slide, torch.nn.dataParallel. Let's see, it's like the 5th line of code there. 4th line of code. So you can wrap around a module to parallelize over multiple GPUs in the batch dimension. So, and this occurs without a lot of work on your part. So you also have nice features like preloaders in PyTorch that allow you to preload the data using multiple workers for parallel processing. So loading your data doesn't swamp your expensive GPUs. Note, however, that the preloaders require a decent amount of work to customize them for your own data set. So if you're working with any of the data sets that PyTorch have available in the preloaders, then it's great, but customizing does take quite a bit of work on your part. All right, so serialization. So serialization is a little bit trickier in PyTorch depending upon your use case. So in the first and recommended way on the slide, the model parameters are saved in a dictionary, then they're serialized and saved to disk. So that binary can then be read by load_state_dict, and then the weights you get in an ordered dict can be then used to inject into the network. So this means that the serialization process is completely ignorant of model structure, but it's also easy to do, and it's pretty lightweight. Because it's ignorant of model structure, you have to have your model architecture when doing inference. So sometimes you don't always have that, and in production it does get a little bit tricky. So the second way is more for the use case of when you want to resume training your model later. So this way you save your model, you don't call eval on it, and then you later get back to training using the pickled model. So note that you'll need to explicitly save the epoch state and the optimizer of your graph to get back to training, but this still doesn't get you the whole way in terms of saving your model because it doesn't save the model architecture either. You still have to have that. So to understand a little bit more what this means, let's think about how Tensorflow saves the model. So with Tensorflow, you can save the entire computational graph as a protocol buffer. And it saves operations, weights, everything you need for inference without needing to deploy your actual source code that exported the protobuffer. This makes it easier to deploy in other languages such as Java, plus it makes backwards compatibility possible. So PyTorch's serialization methods assume that you have that entire model architecture, which you might not have the original source code, right? You just might have maybe the saved model. You might want to also deploy your model into a different language. Luckily, with PyTorch 1.0, you can now do that without using awks. But PyTorch's methods for serialization and deserialization, it makes backwards compatibility an issue in production if you don't have the model architecture. So you have to be very careful about the changes to making changes to your model, because if you don't have that original source code, you could have mismatched model parameters with your new model. Okay, but as I said, luckily with PyTorch 1.0, you can serialize and optimize your models using TorchScript. So this means that you can turn your dynamic computational graph into a static one for optimization and deploy your model to a non-Python environment. So to understand how JIT Script works, let's talk about its cornerstone, the script module, which you can see on the slide. Okay, so the script module, it acts, if you've ever touched PyTorch, it acts in the same capacity as the NN module, where the NN module runs actual Python functions. The script module runs methods as TorchScript, so that's a subset of Python. So that contains built-in tensor operations, and so it doesn't rely on Python. If you're familiar with ONCs, you've actually used trace before because it's been available since PyTorch 0.3, but now you can actually use it to also instantiate your models within PyTorch. So that way you can save your PyTorch model using trace, then deploy it in an environment with JIT load. So JIT trace, which is part of the script module, records operations on tensors as the function is run, and that recording is added as the forward method in script module. So the forward pass operations that are normally regular Python functions are now stored in a DAG, in a static graph, and then you'll provide the inputs. So the recording won't copy control flow ops though, because they are only recording tensor operations. So if you do have any control flow within your model, you actually need to use JIT trace or JIT script instead of JIT trace. All right, so here's an example of using JIT script where we have a basic CNN model. One thing to note is that you will have to provide your own example inputs to trace, which is somewhat similar to how Tensorflow requires placeholder variables, right? Because remember, we're building a static graph. Also, see how we pass in script module instead of, again, the normal NN module. And then we annotate our forward function with a script method decorator. And then, although I didn't show it in this screenshot, we simply use the save method, super simple, and it saves all the methods and parameters of the module to file. So also note that currently you can't make calls in your code to native Python functions if you want to save your model with TorchScript, but as everything with new frameworks, that's all subject to change. All right, so here's an example of deploying the model using Torch JIT load on Algorithmia. You can check out the function called load model at the top, and that's where you load your model using JIT load, and that's it. The rest of the code is just more about image processing and processing your inputs and everything. Note that it was trained and saved using Torch JIT trace, not Torch JIT script, because I wanted the whole model architecture, and I didn't have any control flow. It's a very simple model. I didn't have any control flow in my model architecture. All right, so if you're stuck in an older PyTorch version or models that can't compile to TorchScript, you can try out ONCs, that's Open Neural Network Exchange. You can also, I won't go too deep into that, but I would like to point out here that PyTorch is kind of big. So for deployment into production, we created this PyTorch ergonomics library, and that works for older versions of PyTorch as well, and that's available on PyPy. So a quick rundown on some use cases that PyTorch is a great fit for. I've already mentioned that its natural support of recurrent neural nets is a great use case because RNNs have variable inputs, and due to PyTorch's use of dynamic graphs, RNNs run faster on PyTorch than any other framework. It doesn't, you don't have to use them separate API. So this is always subject to change, as I said, but I haven't seen benchmarks yet comparing TensorFlow eager execution RNN model, only TensorFlow fold, and TensorFlow fold doesn't come close to PyTorch. Also, again, due to the choice of having dynamic graphs versus static graphs, PyTorch is a winner for easy debugging and being able to quickly iterate on your model due to the architecture, the imperative programming structure. It makes it easy. And researchers have been the largest adopters and fans of PyTorch because of this. So when using PyTorch in production, there are a few downsides. One thing to note is that even if you're using PyTorch 1.0, the PyTorch wheels, as I mentioned, are huge, and they take 3 to 5 minutes to unpack. So imagine doing that in a Docker container in production. So that's something to look at too when you're choosing, especially as these two projects kind of converge on their capabilities. Performance is going to be a huge component of looking at which one to use. So, okay, I hope this talk helped you understand areas where you might want to use PyTorch for your projects. A lot of times you're using PyTorch for flexibility, but sometimes losing out on performance, but that depends on your hardware as well. And now that different memory layouts are available in PyTorch, the future is really looking good for PyTorch and performance and production. So again, thank you for coming. If you want to try Algorithmia, that's the promo code and gives you a bunch of free credits to kick the tires. So thanks.